Please switch it back to the remote. Yes. So, yeah, Lisa, please go ahead. Thank you so much for waiting.
Hi, everyone. Good morning from West Coast, United States. It's kind of late afternoon there, so really sorry I couldn't be there in person. I wish I could, but it's still exciting to present remotely. And my name is Lisa Huang. I'm a fourth-year PhD student at UC San Diego. Today, I'll be talking about some really exciting work here in San Diego around live programming and debugging. So debugging is a very normal process of programming, and debugging sometimes can cause pain. So let's check out a few common debugging techniques that might be really familiar to you. The first one is I just did some search online and read some Reddit posts, and apparently one of the most common techniques is console logs or print statements. And the other one would be debugger breakpoints, which is what we see typically in like GDB, or in the screenshot I show it in a browser developer tool as part of Chrome developer tools. So these debugging techniques, however, can be painful in the following aspects. So we all know that debugging is an activity that centers around monitoring state changes in order for the programmer to understand program behavior and find out mismatches in the program behavior to their expectations. And for one to monitor state changes using these common techniques, they will have to insert the print statements or the breakpoints manually, potentially multiple times. You probably have the experience of having 100 print statements or something in the code base, just trying to monitor the state changes and understand what's going on. Another part of the limitations is the preciseness. These insertions of print statements and breakpoints would have to be precise. If you want to see the state change of one location in the code base, you really need a breakpoint or a print statement exactly at that place. And finally, the visual output parsing part. This might be familiar to you. You will have a huge pile of debugging output, and although you try your best formatting it as elegant as possible, you still have a hard time connecting components of that debug output to the corresponding print statements or breakpoints in your program. So to alleviate these challenges, there have been advances in debugging technologies. In our paper, we define these technologies as state-first debugging, or debugging techniques that automatically reveal state information based on some specifications around the state. To make it more concrete, let's look at a few examples. There is the conditional breakpoints, which is a technique that automatically pauses program execution whenever a user's specified condition becomes true. And there's object-centric debugging, which focuses more on the object-oriented programming paradigm. And this technique would automatically pause program execution upon events such as object instantiation, method invocation, etc. But state-first debugging has their limitations as well. And the biggest limitation out there is that they're debuggers at the end of the day, and they're meant to pause program execution. As a result, they force the programmers to only see one state at a time. There's no way for the programmer to step back and take a look at a potentially bigger picture of the program execution at all. Second, there's no explicit visual connection between the program state and the code. It's really hard for one to figure out the exact lines of code in the code base that results in the creation of a program state. And finally, what if you have changes in the code? Well, you have to repeat all these debugging process and the debugging tools, you have to go back to square one and navigate through all the state changes until you reach the point at which you want to inspect. Despite these limitations, we love state-first debugging. We think it's really essential to make state information as transparent as possible to the programmer during debugging. So in our work, we tried to make state-first debugging better. We made it live. In our work, we proposed the paradigm of live state-first debugging, a paradigm in which programmers always see all state changes and their connections to the code. So without further words needed, let's see a live demo of our implementation of live state-first debugging for GUI applications, a system what we call Unfold. I hope I'm showing the application here. Okay, I'm just hoping. Right, so for this demo, I want you to follow the story of Alice. Alice is a web developer working at an e-commerce company. And these companies develop websites, like shopping websites that promote their products and trying to make you spend as much money as possible on their products. And sometimes they would use promotion pop-ups that might be familiar to you as well. You know, as you're scrolling through their website, you sometimes see a pop-up showing up out of nowhere, asking you to sign up for their newsletter in order to receive a 15% off. So this is a precise shopping website that Alice is working on. She just joined the team, so she's still trying to figure out what works in the website, what does not work. And to that end, she decides to use Unfold, which is the interface you're seeing right now, to understand the behavior of the website and to fix the behaviors if they're buggy. So in this interface, you see something that looks like a traditional IDE with code on the side, and you can see the file directory in different tabs or search within the code base. What makes it special is that you can see the actual rendered interface of the web application you're working on the right, without having to switch to a browser tab or a different pane. So Alice uses this tool to pull up the code base of the shopping website. She sees the JavaScript code on the left and the actual website on the right. So her assumption for the behavior of this website is the following. When the user clicks on the background of the website, a pop-up will show up about promotion going on for this website. And if the user decides to click on the close button of the pop-up should disappear. This is our expectation. And let's see what happens. So now I'm Alice. I'm going to click on the background of this website. And I will see that, well, indeed, the pop-up shows up. But at the same time, besides seeing the final UI stage of the website, I also see the intermediate UI stage preceding the final stage in this UI stage timeline. So I can see that the pop-up first shows up, and then later the grayed out-ish background is added at the end. I also noticed that there are some numbered circles on top of each UI state, and they are used to connect visually each UI state and the code that results in their creation. So for example, if I click on the UI state 1, I can see a bigger view of UI state up here in the interface. And I can also see that in the code, line 43 and as a result, line 57 leads to the creation of UI state. So at this point, Alice looks at all the information she sees on the screen, and everything looks pretty good. So she moves on to test out the second user interaction, which is closing the pop-up. And once she clicks on the close button, she expects the pop-up would disappear. But in fact, it does not. And If Alice were using some tool, some traditional debugging tool, all she would see would be the final UI state. And she would be really wondering, like, what's going on? Is my computer freezing, or is the execution not going well so far? But with Unfold, she actually could see the intermediate UI state preceding the final UI state. And with this UI state timeline, you can see that the pop-up did disappear by the end of state 4. It came back on in state 5 and 6. So this is apparently a buggy behavior. But the goal for debugging is very clear to Alice. All she needs to figure out is what code that leads to the creation of state 5 and 6 and prevent those lines of code from executing. So by looking into the code base, and she's looking for numbered circles with numbers 5 and 6, and she realized that function open modal got executed unexpectedly. Supposedly, the open modal function should only be executed when someone clicked on a random background on the website, and only the click event handler for the close button right here, around line 50, should have been executed by the second click event. So what's going on here? I'll jump right into the explanation, since Alice is very expert in web development, and she's familiar with the DOM structure of this web application. It turns out what's going on here is event bubbling. A click event happening on the close button here got bubbled up onto a parent node in a DOM tree, which is the whole website. So to prevent this click event on the close button from bubbling up, it's very easy. All you need to do is add a stop propagation call at the end of that click event handler, so the event would not bubble up. And this is precisely what Alice would decide to do. So she adds in a call to stop propagation to stop the event from bubbling. And as you might notice, as soon as she starts typing, the bubbles inside the code editor turn into a somewhat unreadable color. And this is an indication that the interface she's seeing on the right is no longer in sync with the code on the left. So to refresh the visualization she sees on the right, she needs to save her code changes. And this is what she's doing now. So after saving this code change, the information on the right gets refreshed without her having to repeat the events she had provided. The events are automatically recorded and replayed. And all the information, all the visualization, including the final UI state and the UI state's timeline, got updated corresponding to the code change. So now, with this fix, you can see that the UI states correctly landed on the state that she expected. The pop-up did not show up again. And that is the end of demo. Now back to the presentation. So I want to spend some time talking about the design rationale behind our paradigm and the system, because the design space is really big, and we need to figure out what design goals we want to prioritize so that the system would satisfy user needs as much as possible. And to that end, we ran an exploratory lab study with 5 programmers experienced in this domain. We had each programmer debug one of the 2 buggy JavaScript applications, a table editing application and a to-do list application. And the purpose of the study is not for us to collect evidence to further validate, but for us to explore the design space of our system. So we want the lab study to be as natural as possible so that we can observe programmers' debugging behavior and draw some insights. As such, in the setting, programmers can use any editor or debugging setup that they like. So we ended up seeing people using a variety of different editors, but for debugging setup, they all ended up using either print statements, console logs, or the browser's developer tool for using the debugger. So Our findings imply 3 design goals that we prioritize for our system design. Number 1, our system should support non-interruptive tracing of UI state changes. It should connect output to the code in a visual way. And finally, our system should automate event triggering so that people don't have to repeat providing event sequences in order to debug a certain UI state. And after we design a system with these design goals in mind, we also ran an evaluation, which is a comparative user study, trying to see to what extent our system can help people debug GUI applications. To that end, we ran a comparative user study with 12 participants, and each participant debugged 2 GUI applications, one using Unfold and the other using a traditional browser developer tool. They spent 30 minutes on each application, and each application came with 2 bugs. We randomized the order of the debugging setup as well as the apps to avoid learning effects. And from the study, we collected both quantitative and qualitative data. So quantitative data such as the success and time one participant took to complete a task, and the qualitative data in terms of user feedback on our system and their perceptions. So for quantitative results, while we observed no effect on the success of debugging or on time on fixing bugs that caused by our system, we did observe an effect caused by our system on the time it took participants to locate bugs in one task. If we look closely at the results for the effect on time on locating bugs, in this box plot, you can see the red rectangles correspond to participants using the browser developer tool, while the blue rectangles correspond to participants using Unfold. And our results show that participants debugged slightly faster in the memory game task using Unfold, with a difference of 0.9 minutes. But it debugged significantly faster in the calculator task, with a difference of 15.7 minutes. And the statistical significance have been evaluated using a Wilcoxon sign rank test on the medians of the values. In terms of user perceptions, we saw that participants found Unfold easy to understand and use. They found it helpful for debugging. But we also saw a lot of desire for customizable inspection of UI states. So here are some concrete real suggestions that came from our participants. Participants wanted to inspect non-visual states in a rather visual way. They wanted to filter out unintentional UI states and connector labels when there are too many of them. They like to examine UI components, tell particular UI state, and they also want to adjust the granularity of information displayed on the screen. So reflecting on our user evaluation results, as well as our overall system and paradigm design, here are some future work ideas and reflections we'd like to discuss with the audience and the community. So the first future work idea is a live debugger that just fixes. Recap, from our study, we observed no effect caused by our system on the success or time of fixing bugs. And this makes sense because debuggers might be helpful for locating bugs, but they don't really suggest code fixes. Current technology include code repair works that help the user to suggest code fixes, but in existing code repair technologies, user is unable to preview the effect of the repair suggestions. We found live programming to be a really promising direction for the user to understand better the effect of fixed suggestions and further tweak on the suggestions. And so for future work, we propose a more live preview in a debugger setting where the debugger suggests code fix suggestions, and the user can use live programming to preview the suggestions. And as a matter of fact, there has been some ongoing work, really exciting, at UC San Diego that works around the space, live programming, and validating those suggestions. And I'd be happy to talk more about that offline. The second future work idea we have is the use of more human-centered design in live programming systems. What we observed from our user study is that users provided rather positive perceptions to our subsystem. This is great because we can see that human-centered design really works. Remember, we designed our system through a formative study that ground our design in the study findings. On the other hand, we also observed some effect caused by our system on the time on locating bugs, but only in one task, not the other. So these results made me wonder, what happened? What happened in that task? Why did people locate bugs faster in one task and not the other? So directly to our project, the next part of future work we plan to do is to dive deeper into the user behavior data that we collected. We want to understand the success and failure lessons here better. Why do people locate bugs faster in one task, and why do people not debug faster in another task? But taking a step back, looking at live programming systems in general, and we'd like to propose a message to the overall live programming community. We see that there's currently more understanding needed for the usability of live programming systems, especially existing systems. And for future work, we'd like to propose a more qualitative evaluation of live programming systems in general, so we can reflect more on the existing designs and think more about possible improvements. Finally, this is not necessarily a future work idea, but some open problem domain we noticed that we really don't have answers for. So I like to pose up here, pose a few open questions so that the audience might find it interesting to think about. Scalable live programming. Why do we need this? What we observed from the user set is a desire for more customizable inspection of the visual information displayed on the screen. We also know that with customizability, here comes the scalability problem. And scalability in live programming has been an open issue for many, many years. So a few open questions we have here are the following. How do you want to tackle liveness for larger and more complex systems? How do we want to support live programming or live state first debugging for program state that does not come with its default visual representation? And how do we want to enable liveness for domains where viewing program behavior can be really useful, such as systems programming, server development, and CI/CD workflows, such as GitHub Actions. So with these open questions in mind, I'd like to wrap up my talk. In summary, we introduced the paradigm of live state-first debugging and its implementation for JavaScript GUI apps, Unfold. We demonstrated through user evaluation that Unfold made locating some bugs faster for users, and it was perceived positively. We proposed a few future work ideas, including liveness for previewing bug fixes, human-centered live programming, and we posed open questions around scalable live state-first debugging. And that is the end of my talk. I thank you for your attention, and I'm ready to take questions. Oh, by the way, if you want to take a deeper dive into our work, here's the link to our paper.
Right. Mike's over here. Hi. It's very nice work, and it looks like it's probably quite useful.
but why do you call this state-first debugging? All debugging's about state. That title doesn't really work for me. To me, I would call this some sort of UI replay, replay UI replay debugging or something. So my criticism is think about the title.
Good question. So I think it makes sense to maybe go back to the slide a little bit. We're calling the line of work around conditional breakpoints and object-centered debugging as state-first debugging in the sense that we think techniques like print statements and traditional breakpoints away forcing the programmers to probe into program execution in order to get the state information. Whereas in these techniques, there's no need of execution probing. You just have the state information available in front of you, taking them for granted. So that's the biggest difference we observe between these state-first systems and execution-first systems, and hence the definitions we assign to these two different categories of debugging paradigms. Does that answer your question?
Hi, thank you so much. That was really great talk, and I never thought I would be so excited about debugging. I wanted to ask if you've thought about using this kind of debugging in a non-UI scenario. So obviously, this seems great for working with UI code, but what about when there's no UI or there's stuff that's a bit hidden? Has that ever come across your mind?
Yeah, that's a really great question. And so in this work, we started off with UI states because these visual representations are just available and we could just take them for granted. Each DOM tree will be visually rendered to some UI representation, fairly easy. But in terms of non-visual information, I think there could be some work around more generic techniques of creating visual representations for such information. In terms of how those generic techniques or how those generic representations might look like, I don't have a concrete idea now, unfortunately, but I do think that is a super interesting line of future work to pursue if we do want to enable state-first debugging to more, or live state-first debugging to more generic domains.
Sorry, this is not a question. I just wanted to follow up on that previous question and mention a bit of related work that I think would be very interesting to this community, which is this project called Z-Step 95 by Henry Lieberman. And they define diagrams off of program state and sort of have the idea of stepping between those states. And I wonder if you could apply that idea to solve this problem of if you don't have a UI, you can create another visual representation and sort of use that as your unit of stepping.
Yeah, that is definitely a promising direction. I am aware of that paper. It's really exciting work. And it's, I guess, trying to refresh my mind about that paper, and I really investigate deeper about how they represent non-visual information on the screen.
Hi, great work. I also got enthusiastic about debugging, but I was already enthusiastic about it. So your work ties this going back in time and replaying events to live programming, which I think is correct. But I didn't read your full paper yet. I only just got the link. But I think this is also called omniscient debugging, this going back in time and replaying, and that could be more related work to add. So, but great work. Thanks for the talk.
Yeah, thanks for the feedback.
Okay.